I'm back with the second half of section 10. Now, we've gotten through all the introductory stuff, and we're down to let's run through an example. So I've got a picture of what I was talking about, where there's a mass on a frictionless surface connected. It's the thing I was talking about earlier. I put some specific numbers on it. Well, a specific number, you got 2 kilograms there. So you pull it 20 centimeters to the side, which actually has no effect on part A. This does, though. If you take the thing and you turn it sideways so that the weight of the thing stretches the spring out, it tells you that that's going to stretch the spring by 39.2 centimeters. So that tells us, you know, if this much weight stretches it that far, we can use Hooke's law to get the spring constant. Once you know the spring constant, if we were given the mass, we can get the frequency from the square root of k over m. So that's the strategy for part A, at least. For part B, the period is just the reciprocal of the frequency. So B is quick once you have A. We'll get back to part C in a moment, but in the details. Part A, it's still over there actually, from the end of the previous focus. Thank you. From the end of the previous recording, the frequency of a harmonic oscillator is the square root of k over m. Well, in cycles per second, it's 1 over 2 pi. Square root of k over m. We know m, but we need k. And let's be clear on the notation, because I'm going to be flinging the letter F around in various forms here. Capital F will be the force for Hooke's law. Little f stands for frequency, the thing that I'm trying to calculate. Hooke's law. Well, if you take the direction into account, it's F equals minus kx, but notice I didn't put the little vector symbols over the F and the X. I'm talking here about the magnitudes of these things. Magnitude of a vector is always a positive number. So magnitude of the force equals the spring constant times the magnitude of the displacement. Rearranging k equals F over X. Now, hopefully by now, I mean, this is the 10th week of the course. Hopefully by now you aren't making that mistake about weight versus mass. The amount of weight hanging on the end of that spring when you let it hang vertically is 19.6 newtons, not 2 kilograms. And what do you know? It just happens to come out an even number. When I wrote the question, I was in the mood to have an even number for the stiffness constant. So now that I know that, little f, the frequency, 1 over 2 pi square root of 50 newtons per meter divided by the 2 kilograms. Fifty divided by 2 is 25. The square root of 25 is 5. And maybe I should have written out the units, but newtons per meter divided by kilograms is going to just leave you with, well, inside the square root, you'd have seconds to the minus 2 power. After you take the square root, seconds to the minus 1 power. We're going to need omega later on. So let's notice as we go by that the angular frequency, the frequency in radians per second, is 5. You divide that by 2 pi, 0.796 of a hertz. 0.796 cycles per second, if you prefer. So that was part A. Part B asks for the period. Period is the reciprocal of the frequency. So while that's still on your calculator, you just push the 1 over x button. Roughly 1 1/4 seconds. What this means, once again, is that in 1 second, it gets just under 0.8 of the way through 1 vibration. 1 vibration takes 1.26 seconds. The last thing it asks for, I won't bother pointing you at the paper here again, but part C says to find the displacement at t equals 0.4 seconds. So for this, you would go back into the, go back in your notes a few pages or go back to the formula sheet and get the function for x as a function of time. X is the displacement, and I showed earlier that x equals a cosine of omega t plus the phase angle. We need to fill some things into that. And x is what the question's asking for. X is how far it's displaced from equilibrium. So we need to fill in numbers for everything else and calculate x. I know that the amplitude is 20 centimeters because it says it was displaced 20 centimeters, then released. Amplitude means the maximum displacement. And if you release it from rest, the place where you did that is as far from equilibrium as it's ever going to get. So that's how I know the amplitude is from that part of the question there, where it says it was released at x equals 20. So a equals 20 times the cosine of remember, I just pointed out as we were going by back here, omega is equal to 5. I said, yeah, we're going to need that in a minute. So that's why I kind of highlighted that. Here's where I wanted it. So that comes from part A. And I'd like to write it as a function of time and then fill in t after that. So for the moment, we'll just leave that t. As for the phase angle, the question says it was released at t equals 0. Well, if it's at its maximum displacement at t equals 0, that's what a cosine function does all by itself without any phase angle to slide it one way or the other. So because it's released at t equals 0, that's how I knew to put in a 0 for the phase angle. And if I was just interested in going right straight for the answer, I suppose I didn't need to bother writing this down again. I could have just stuck the time in along with all these other numbers and punched it up, but I thought it would be good to point out how the units work. Time will be in seconds. Seconds times seconds to the -1 power leaves you with a dimensionless number. Any transcendental function, whether it's a trig function, whether it's a logarithm, whether it's an exponential, whether it's a hyperbolic function, blah, blah, blah. Any transcendental function has to have a dimensionless number for its argument. And so that's what indeed happens here. Seconds over seconds cancels out. As far as getting through practical problem solving without making a mistake, notice that it's going to be the cosine of a certain number of radians. Okay, a dimensionless number, that's an angle in radians. One place where I use some red ink, people have their calculator in degree mode and don't realize it. As far as this goes, a function not only needs a dimensionless number for its argument, but it also delivers up a dimensionless number when you calculated the function. So I don't have to convert this into meters as long as I don't mind having the answer in centimeters. Okay, whatever unit is on the amplitude, that unit times a dimensionless number is going to give me x in that unit. I could have it in, well, never mind inches, you could have it in cubits if you wanted to go really old school. Whatever that is, that's going to be, it'll work. So at t equals t equals 0.4, we've got 20 centimeters times the cosine five times 0.4 would be 2. If you did get your calculator in radian mode, you should be getting negative 0.4161 for the cosine of 2 radians. Make sure I'm not going off the edge of the screen. The minus sign means that at the moment, the mass is located on the other side of equilibrium from where it started. Incidentally, for anybody who is wondering, a cubit means from there to there. Standard cubit is 18 inches, but if you're building an ark 3,000 or 4,000 years ago, that's just from there to there is a cubit. Well, let's turn the page and see what other sorts of trouble I can get myself into here. A simple pendulum. Straighter like that, I guess. A simple pendulum is a point-like mass on the end of a massless string. Well, of course, massless means that the string is maybe 1/2 or 3/4 of a gram, and you've got maybe 200 grams hanging on the end of it, so that by comparison, the mass of the string might as well be 0. It's not going to affect the answer to the level of accuracy we care about. At the moment, the pendulum is displaced by an angle theta from the vertical, or if you prefer to think in terms of distances instead of angles, the mass, the so-called bob of the pendulum, it swings back and forth along a circular arc, and S is the arc length. It's the distance from equilibrium measured along its curved path there. So it's going to vibrate, okay? You pull the thing to the side, you let go of it, it goes back and forth, kind of like the mass bouncing on a spring goes back and forth. Pendula, by the way, were once a very big deal because until, I think the first electric clocks appeared in maybe the 1930s or sometime like that, but for several hundred years, clocks regulated by a pendulum were state-of-the-art technology. And timekeeping is a big deal if you start talking about navigation, okay? The British Empire was built on navigation. The British Navy went out and took over the world, basically. Well, not the whole world, but a pretty good chunk of it. Well, if you're on a ship, it's kind of useful to know where the heck you are if you're out sailing around someplace where you can't see any land. Your latitude is fairly easy. It's just the altitude, well, it's approximately the altitude of the North Star. To calculate your longitude, well, today to get your longitude, you buy a $20 GPS unit, and it'll tell you where you are to within about 10 feet. But at one time, in order to calculate your longitude by dead reckoning, you had to know what time it is. You'd have to measure where the stars are, a couple of stars at least, and then you have to know exactly what time those observations were taken. And from that, you could figure out where you're located. Well, in the early 1700s, there was no way to, nobody knew how to build a clock that would keep accurate time on a moving ship, okay? It's one thing to set a clock on the mantle and have it tell you what time it is, but a ship, even on a good day, is kind of rolling around, and how are you gonna get a clock to work properly like that? There was actually a big prize that the British Crown put up for somebody who would invent a clock like that. And then, of course, the whole thing turned into a huge mess. It was, I can't remember his first name. The guy's last name was Harrison. Had succeeded in building such a clock, but then they wouldn't give him the prize, and it turned into, anyhow, I digress. The point is, a pendulum was a very important piece of technology at one time. Maybe not so much today, but it's still worth looking at because as I analyze it, it's going to make one or two important points. So as this thing goes back and forth, Does it obey all of these equations? You know, this stuff that's behind me written all over the blackboard here. Does that apply to this pendulum like it does to a mass on a spring? Well, it depends. If the pendulum is in fact a harmonic oscillator, in other words, if the restoring force on it is linear, if it obeys Hooke's law, then yes, everything I've already said applies to this pendulum. But, well, that's what we have to do, is we have to look at the forces on this thing and see if the restoring force is actually linear. Does it obey Hooke's law? And if it does, then we've already got it all figured out. So, you know, the frequency would be that, and so forth. So here's our pendulum. There's part of the circular arc that it's traveling along as it goes back and forth. And at this particular moment, the mass is located right there. There are two forces that act on the pendulum. There's the string, T for tension. The string at any time will lie along a radius. Okay, the point that the pendulum is suspended from is at the center of this circular arc, and the string goes from there to the mass right along a radius. So this is perpendicular to the direction of motion. This force does nothing to speed it up or slow it down because it acts sideways relative to the direction of motion. The only other force is the weight. Just like I did on an inclined plane, the convenient thing to do here is to resolve the forces into components, not horizontally and vertically, but rather along and across the direction of motion. In other words, radial and tangential components rather than horizontal and vertical. So using the parallelogram rule to kind of represent components, this would be the tangential component of the weight, and this would be the radial component. Well, on the original picture on the paper over there, theta was the angle between the string and a vertical line. That would be the same as this angle here, which would be the same as this angle here. So this tangential component is mg sine of theta. The hypotenuse is mg, and this is the opposite side, opposite from the angle theta. So hypotenuse times sine is the opposite side. This is the restoring force. That's what's pulling the mass toward equilibrium. That's the force, you know, along the direction of motion. So, does that look like Hooke's law? It's looking kind of doubtful, but Hooke's law is a relationship I'll need to make a substitution, but maybe I should write down some of what I've already said. motion is harmonic if the restoring force obeys Hooke's law. The restoring force being this component of the pendulum's weight. So I'll call it FR for restoring force. And I stuck a minus sign in it just to kind of make it look like Hooke's law. Mg sine of theta. So to get it in terms of distance instead of an angle, we've got from, you know, the picture on the handout there, it looked like this. That's theta, and I called the length of the string L for length, and this is S. Well, remember from, I believe it was section 7, arc length is related to the angle it subtends by S equals R theta. Well, in this case, the radius, I called it L for the length of the string. So theta equals S over R, where in this case, R is equal to L the length of the pendulum. So you can see, if I stick that in here, the force is not proportional to the distance. It's proportional to the sine of the distance. Well, the distance over L, okay? So the answer is no. A pendulum is a nonlinear oscillator, and it does all sorts of things that no self-respecting harmonic oscillator would do. But what if we make a little agreement among ourselves to keep the amplitude small, okay? When you've got this weight hanging here on the string, and what if I said, all I'm going to do is pull this just a tiny bit to one side and then let go of it, so that instead of swinging back and forth like that, you've just got the thing kind of going a little bit back and forth. If theta is small, which is by no means guaranteed, you remember the small angle approximations from some math class. At small angles, sine theta will be equal to theta in radians, okay? How small, I put it in quotation marks because how small is small? Well, that depends on how many decimal places you want to go to, okay? And actually, I spent a little time one day with a calculator figuring out just how far you could go and get away with it. If all you want for your numbers is 2 significant figures, you can get this to work out to 18 degrees. If you want 3 significant figures, this will work to 4 degrees. If you want 4 significant figures, this will work to 1 3/4 degrees. And that's where I stopped. But, you know, the more precise you want to be, the smaller small means, okay? But for any level, you know, any number of decimal places that you want to go to, there is a sufficiently small angle where you could make this true, that it would not affect your answer within the level of accuracy that you care about. So the restoring force then would equal, instead of mg sine of theta, if sine theta equals theta, you just have that, making this substitution for theta. And there we do have Hooke's law. Rearranging the parentheses a little bit. There it is. Restoring force equals some constant times the distance from equilibrium. That's Hooke's law. So a pendulum is harmonic for small amplitudes only. And I guess the biggest reason I have for going through this is because this is typical for a lot of real world systems. If you look at the infrared spectra of molecules, you've got a container full of carbon monoxide gas. The infrared lines in the spectrum come from vibrational states. The carbon and the oxygen molecule are vibrating like that, okay? The spring, in quotation marks, is the chemical bond between the two atoms, and the atoms vibrate in the molecule. And if you get into quantum mechanics, harmonic oscillators have energy levels, okay? As the molecule jumps from one energy level to another, it will absorb or emit infrared light. Well, the molecule is almost harmonic, but not quite. Just like with this pendulum, the restoring force can be approximated as something linear if you want to simplify your calculations. But in the real world, it's close to linear, but not quite. And there are other situations where it's the same story. So this is meant as an example of how a harmonic oscillator can be used as sort of an idealized approximation to how real things vibrate. And sometimes you can say they're approximately linear as long as you don't let the amplitude get too big. So that's kind of the point of this story. But if it is a small amplitude pendulum, the thing in parentheses there would be, from Hooke's law, F equals kx, or in this case, it's S because it's an arc length instead of along an x-axis. F equals k times the distance. This thing in parentheses would be k, which it doesn't seem quite right to call it a spring constant when there isn't any spring. So maybe force constant. So a pendulum is harmonic only for small vibrations. You would do well to keep that in mind as you do the lab. If the amplitude is in fact small. Well, the frequency of a harmonic oscillator is 1 over 2 pi squared of k over m. And I just got done showing that for a small amplitude pendulum, k is mg over L. So we'll stick that in there. And then a sort of an interesting thing happens. The mass drops out. Frequency is just 1 over 2 pi square root of g over L. And if you want to look at it the other way around, the period would be the reciprocal of that. For a mass on a spring, as I said earlier, if the mass somehow gets heavier, that slows it down. Additional mass equals additional inertia, slows it down, makes the period longer. For this, however, if you've got some little 20-gram mass on the end of the string, or if it's a 200-gram mass on the end of the string, the period will be exactly the same. Because on the one hand, with the 200-gram mass, it's got 10 times as much inertia. But on the other hand, it's gravity that makes the thing move. And if you've got 10 times as much mass, gravity pulls 10 times as hard. So 10 times as big a force acting on 10 times as much inertia, they balance out. And so just like with a free-falling object, the mass doesn't matter. All that it matters is the length of the pendulum and the strength of the gravitational field you're in, which suggests, well, that's a mess, isn't it? Okay, that's better. Which suggests a much simpler way of measuring the gravitational acceleration than the way we did it at the beginning of the semester. Remember, there was that lab where there was the tower that drops the weight, and as it falls, we passed the electric sparks through it, and you measured up where all the dots were, and you drew a graph and the slope of the graph. And that works pretty well. It gives you G to usually within about 3% or so. But actually, all you need is just hunt around for some sort of a mass, like, you know, an old bolt or something like that. Hang it on the end of a piece of yarn, get it vibrating with a small amplitude, because none of this is valid at large amplitudes. And you just sit there and you time the period. And if you let the clock run a long time, like if you do, this is the idea behind the next sample problem that I'll get to in a minute. If you time something like 100 periods, that will make the percentage of uncertainty very small, and you'll be able to measure G at least as accurately as we did with that device that we used in Lab 1B. But I've got a couple more things to write down before I get to the sample problem. So frequency of a pendulum, period is just the reciprocal of the frequency. Position is a function of time. Again, adapting the equation that I had earlier for a harmonic oscillator. The position of a harmonic oscillator oscillator is a cosine of omega t plus the phase angle. And I just showed up here that omega, which is equal to 2 pi f, omega is the square root of g over L. So now it's time to point the camera at the next problem. Except the next problem is a little higher up the page than I thought it was. Okay, that works. So using a pendulum to measure the gravitational acceleration. The longer the pendulum, the better, because if you're off by a few millimeters, a greater length reduces the percentage of uncertainty coming from that measurement. And the longer you can run the clock, the better, because your reaction time with the clock is going to make that off probably by a few tenths of a second. And so the larger the time interval is, the smaller a percentage that becomes. So a fairly long pendulum, a lot of cycles, and it doesn't take very long, actually. It's just a few lines of calculations. So from the information given in the question, you can determine either the frequency or the period, whichever one is your favorite formula. It doesn't matter which way you look at it. I did it with the frequency. There isn't exactly a formula on the formula sheet that I'm using here. You just simply have to understand what the frequency is. Frequency is the number of cycles per second. Anytime you encounter the word per, that means divide. Miles per hour is miles divided by hours. Cycles per second is cycles divided by seconds. So based on the measurements, dealing with a frequency just a little under half a hertz. So if I think what's given, I'd have to look at it to say for sure, but I'm pretty sure what I put on the formula sheet was the formula for omega rather than the formula for f. And somewhere next to it, it probably says omega equals 2 pi f. But anyhow, omega, the angular frequency, is the square root of g over L, which a couple lines of algebra to solve it for the thing that we're looking for. The question asks for g, because see, the local value of g varies a little bit from one place to another, even on the surface of the Earth. So in the particular place where this experiment was done, what is the local value of g? So you square both sides and then you multiply both sides by L. And that's what we're going to want to drop our numbers into. Length of the pendulum. One meter. And put in the frequency, you punch it up. Looks like the local value in this particular location is 9.81. Next thing down the page. Look that way. Elastic potential energy. I'm not going to bother focusing with that because I'm just going to go right back to the blackboard anyhow, but the fuzz there says elastic potential energy. Potential energy in general, remember, equals the work that an object could do because of its position. And the example we looked at earlier in the course was gravitational potential energy. You have an object that's elevated in a gravitational field. The higher it's elevated, the more work it's capable of doing as it falls. So, gravitational potential energy. For elastic potential energy, we're considering an object attached to a spring instead of an object attached to a gravitational field. The potential energy would be the work that it could do in returning to equilibrium. This is a little more complicated than the gravitational case, though, because as an object falls, gravity provides a constant force. The force is mg here, it's still mg here, it's still mg down there. With a spring, you're dealing with the Hooke's law force. How big the force is changes as x changes. So rather than just saying force times distance, you have to take the entire displacement and divide it up into little increments. So here is this frictionless surface once again. And that spring looks like it's definitely been stretched beyond its elastic limit, but, well, this wasn't meant to be a particularly accurate picture. Anyhow, maybe the equilibrium position is over here. And at the moment, the mass is located there. And so that's the displacement of that mass, x. And the spring is pulling on it with a force F. And as the restoring force pulls it back toward equilibrium, let's consider just, does that even show up? Well, it does when I get my head out of the way. Just a very small amount of movement, okay? X is from there to there. This is how much X changes. You know, D for difference, as the thing goes from there to there. So what you have to do when you deal with a variable force is you take the entire displacement, you know, as the mass goes from there to there, you have to take that and chop it up into lots of little pieces, each so small that the force can be considered constant. And you do the force times the distance in each little piece, and then add all those up to get the total. Of course, that's just an approximation, because even in that small amount of movement there, the force changes a little bit. It becomes a better approximation if you use a larger number of smaller increments. The approximation becomes exact if you take the limit of infinitely many, infinitely small pieces, and that's called integrating. But back back to the definition here. Elastic potential energy means elastic potential energy means the work it being this object, the work it could do returning to equilibrium. Just like gravitational potential energy means the work that this eraser could do returning to the floor, the work that this could do returning to equilibrium is the elastic potential energy. In other words, the energy stored in that stretched spring. Work, if you have a constant force, is just the force times the distance. Then there's also the cosine factor. If you're going to divide it into lots of little increments like I was talking about, it becomes the integral of f dot ds. There are minus signs that are more trouble to explain than they're worth. Like, for example, there's the cosine of 180 degrees and the, well, no, not the way I've drawn it, but let's just say, to try and get to the point here before it gets to be tomorrow, we're going to play kind of sloppy with the minus signs. So overlooking some minus signs, such as the minus in Hooke's law, for example. The minus signs cancel each other out by the time you get to the answer anyhow, so work done in each infinitesimal displacement, ds, is the dot product of the force and that displacement. And an integral is a summation, okay? It's a sum of infinitely many continuously distributed infinitesimals. So add up the work done in each little increment. And in this case, the force is provided by Hooke's law. Since the mass is sliding along the x-axis, ds is the same thing as dx. K is a constant, so you can take it out in front of the integral. And if I wasn't trying to keep it quick and to the point, I should have been doing a definite integral where you had, well, anyhow, you end up with x to the first integrates to 1/2 x squared. So the moral of the story is U for potential energy. When it was gravitational, I put a G subscript on it. I don't want to use an E for elastic because when we get back in January, there'll be electric potential energy, and that starts with E also. So how about S for a spring, okay? The energy stored in a spring. One half kx squared. Three examples, and that'll be the rest of section 10. So first of all, number 4, you've got this spring hanging vertically, and you walk up with a 500-gram mass in your hand, and you hook it on there, and you let go. And the question is, how fast is that mass moving when it's 2 centimeters below the point where you dropped it from? This is going to be I mean, a lot of these problems, there's more than one way of doing them, but the way I'm going to approach it anyhow, it's a conservation of energy problem. There's no friction, assuming there's no friction. So E initial will equal E final. No work done by friction in between. So total mechanical energy means kinetic energy plus potential energy. Kinetic energy is 1/2 mv squared. There's no rotation going on to complicate that. But as far as potential energy, in this problem, we are dealing with 2 different kinds of potential energy. There are 2 conservative forces acting on that mass as it moves, gravity and the elastic force from the spring. So the total potential energy will be the elastic potential energy plus the gravitational potential energy. So those 3 things added together, that's the total mechanical energy. That's the thing that will be equal to the same thing before and after. E initial equals E final, because there's no non-conservative forces present to change it. When you first release the mass, the velocity is 0 because you released it from rest. X equals 0. X means how far is the spring stretched or compressed, and you release the thing from its equilibrium position. As for the gravitational energy, well, you can measure H from any place that seems convenient. One good choice might be to measure it from the final position. That would make a lot of sense, but I think it makes just as much sense to measure H from the same place that you're measuring X, in which case that would also start out 0. So if you look at things that way, the initial energy is going to be 0 plus 0 plus 0. And what happens as the thing falls is the farther it goes, the more negative this term becomes. Gravitational energy decreases as it falls. And these 2 terms, which are incapable of being negative, they become more and more positive as this gets more and more negative. And that's how you keep the total the same. So E initial is equal to 0 because I've decided to let H equals 0. Where X equals 0, which means that's where the spring is not stretched. 1/2 mv squared. The mass is 1/2 kilogram. I guess I didn't really want a parenthesis there, did I? V is my unknown. I'm trying to figure out how fast it's going at that moment. In the elastic potential energy term, I guess I don't need to put the unit on it. It takes up space. put the unit on X though, because I've converted from centimeters into meters. So the question gives us the spring constant. And in the end, the spring has been stretched out 2 centimeters. The minus sign's irrelevant because you're going to square it. I didn't really need to write it down, but I just thought it would look good if it matched what I put in for H. Half a kilogram, this is the MGH term now, half a kilogram times 9.8 times 2 centimeters below the point where it started. And then there's some math. 0.25 v squared. The 1/2 kx squared term comes out 0.08. And the MGH term comes out 0.098. So you've got that minus that is negative 0.018. You add it to both sides. And then divide through by the 0.25, take the square root. So at that particular moment, the thing is moving at 0.268 of a meter per second. Back to the handout. So one more time, we have the mass sliding back and forth on the frictionless air track due to a spring connected to it. And it gives the amplitude. Find the speed when it's 17 centimeters from equilibrium. Well, as with many problems, there's more than one way of doing this. You can go after, there was those equations for V equals V max times all of that, and where V max equals omega times A. And you can go at it with those equations, and that's, if you do it right, that'll work. I think it's a little more straightforward, possibly, to use conservation of energy. That's the way I'm going to do it. But like I said, you can get to the right answer more than one way, as is the case with many types of problems. This time, kinetic plus potential is just that, because it's moving on a horizontal surface. There's never any change in the gravitational potential energy. The smart thing to do would be measure your heights from the level where it is all the time, and that just makes initial and final gravitational energy 0, okay? So because it never changes its elevation, there is no MGH term. And because we're assuming a frictionless situation, the energy at x equals 17 would be equal to the energy at x equals 30. conservation of energy, where each of these E's is given by the thing I wrote above it. So to the left of the equals, 1/2 the mass. This is what we're looking for. The question says, phrase it, find its speed when 17 centimeters from equilibrium. So the speed at x equals 17, that's what we want to solve for. Then we have the potential energy term, 1/2 kx squared. Over on the other side, 30 centimeters is the amplitude, okay? 30 centimeters is the farthest from equilibrium it ever gets. That's where the thing turns around and starts going back. So at that instant, when it's there, the velocity passes through 0 at that time. So there is no kinetic energy. When it gets out to either side there, the turning points on either side of equilibrium, all of the energy is in the form of potential energy at that instant, because for just an instant, the velocity passes through 0. So 0 for the kinetic energy, and 1/2 kx squared, except I'm going to call x a, because that's what the word amplitude means in the first place. The maximum displacement is the definition of amplitude. X is the displacement, and 30 is the maximum value, okay? So x equals a at that moment. Now I could throw numbers into this at this point, but I wanna manipulate it around with letters for a couple of lines, just because that'll set things up nicely for the last problem, which is sort of a continuation of this one. So I'm going to save throwing the numbers in for the very end. But one thing I can do that'll clean it up, I can multiply through by 2 and get rid of all those 1/2s that are everywhere. I'm going to also divide through by m. I'm looking for v, so what I'm working toward here is to solve it for v, make it say v equals something. So if I'm trying to solve it for v, it would make sense to subtract this from both sides. I kind of did two things at once there to speed things up and save a little time and a little space on the page. I subtracted this term from both sides, and then after I did that, I used the distributive property to factor out the k over m. So k over m times a squared minus k over m times x squared. And finally, you would take the square root, and that's the point at which I'm going to drop in the numbers. For k, the question gives us a 100. That's written on the picture right next to the spring. The mass, 0.25 of a kilogram. The amplitude is 0.3 of a meter. X over here is 17 centimeters, 0.17 of a meter. And so you do all that, and when the smoke clears, you've got 4.94 meters per second. one more, and then I'm going to go have lunch. Standing here talking for close to 3 hours. Well, more like 2.5, but just between you and me, it's getting a little tedious. I'm about ready to do something else for a few minutes. But I think I'll come back this afternoon and get at least the first half of section 11 done. So, continuing number 5, same oscillator. The question is, how much does the speed change between x equals 17 and x equals 17.01? The main thing I wanted to illustrate with this example is how you can use differentials to approximate small differences. Something that's actually come up a couple of times before in the labs when doing the experimental uncertainties, okay? How far off might you be based on, from some formula based on how far off the numbers you put in are? Well, you assume that they're not off by too much. You're looking at just small differences, and you can approximate those small differences by differentials. We did that, for example, in the conservation of momentum lab. And the force table lab was another one. So same sort of thing here. The difference between 17 and 17.01, that's a pretty small difference. And there's a problem in the homework like this also. The problem that one involves the period of a pendulum, if I remember right. And it's got a part A and it's got a part B. And for the one part, you're supposed to, the idea is you take the pendulum from like the bottom of a mountain to the top where there's a slight difference in the local value of gravity. And how much does it change the period of the pendulum is the question. And one part of the quiz says to find the difference just by a brute force method, where you calculate the period both places and then subtract to get the difference. And then the other part, I forget which one is A and which one is B, but the other part says to approximate the small change with a differential, like I'm going to do in this example here. And what does that say the change in the period will be? And if you do it correctly, you get exactly the same answer both ways. But anyhow. Actually, before I get into number 6, hopefully it's a review of of the calculus I'm talking about here, but I have found people quite often are, at least at this point in their education, are a little fuzzy on the difference between a derivative and a differential. So maybe just a quick aside about that. Say you've got, functions don't get too much simpler than that, okay? Your basic garden variety parabola, y equals x squared. If you take the derivative of that function, the derivative of y with respect to x, well, you bring down the old exponent and the new one is, you reduce it by 1. Derivative of x squared is 2x. For comparison, the differential is just dy. You aren't differentiating with respect to anything, okay? It's just dy rather than dy over dx. What it looks like is I took the dx and multiplied both sides, but actually it's not an algebraic process. This is actually the chain rule, okay? The derivative, maybe it would be better if I wrote it with parentheses like that. The derivative of what's outside the parentheses, or actually, in this case, the differential. The differential of what's outside the parentheses, that would be 2x, times the differential of what's inside the parentheses, that's the dx. Okay, so this is actually here because of the chain rule rather than some algebraic process. Actually, the chain rule applies here also, but when you do the derivative of what's inside the parentheses, that's equal to dx over dx, which is just equal to 1, and so nobody ever bothers to write it down. But anyhow, that's the distinction between a derivative and a differential. Now, a differential actually means an infinitesimal amount of difference. You're taking the limit as dx and dy approach 0. But that can be used as an approximation for differences that are small but finite. It's an approximation because it's not really a differential unless you're taking the limit. But anyhow, number 6. From the previous problem, we had v squared equals k over m a squared minus k over m x squared. See, that's what it said back there. I just distributed the k over m because I liked it better that way. Here's where we take the differential. Just like I did with x squared, only now it's a v instead of an x. We've got two v dv. The dv comes from the chain rule, like I was saying back up here. This term, those are all constants. Sometimes it's hard to tell just because it's all letters, you know, but the spring constant, that sounds like a constant. The mass, the amplitude, those are all just numbers. And the derivative of a constant is 0. K over m, those are constants, so they just get recopied. The differential of x squared, 2x dx. Exactly what I was talking about up here. We can simplify it slightly if we divide the equation through by 2. 2 over 2 here, 2 over 2 there. dv is the thing I'm looking for this time. The question says, how much does the speed change? Okay, the difference between the initial and final speed, dv. So that's what I want to solve it for. dv equals minus kx, okay, kx dx on top. On the bottom, we've got the mass, and also I've divided both sides by v, so that'll be down under there also. And I wish I left myself I'm going to write this a little lower so I've got some space to write around it. Spring constant, 100, given in the question. For x, well, x changes a little bit. It goes from 17 to 17.01. If you aren't too concerned about being accurate, you can just say that's pretty much 17 the whole time and stick a 17 in there, and that'll work reasonably well. But the ideal thing would be to go for the midpoint, okay? halfway between 17 and 17.01 would be 17.005 centimeters, or actually, I need meters here, so while 0.17 is probably close enough, really the best thing would be the midpoint of the interval. And then for dx, that's the difference. The difference between 17 and 17.01 would be the 0.01 of a centimeter, or 0.0001 of a meter. I should write down where I got that from. 0.1701 minus 0.1700. dx, the difference in x, is you subtract them. Down on the bottom, the mass, 0.25. And the velocity, well, there again, it changes slightly, but not very much. We'll just stick in the answer from the previous question. So, punch all that up. We've got a decimal, 2 zeros, 1, 3, 8. Negative because it's losing speed. With any kind of a change, increases are positive, decreases are negative. Some of you might like to just rely on brute force methods and say, look, if I ever encounter something like this, I'll just calculate the speed at the two different places and subtract. That might take a little bit longer, but not an awful lot longer. Where that would get you in trouble is if you're looking at something where the amount of change is so small. Okay, here it was only a decimal point and 2 zeros. If the answer was something like a decimal point and 10 zeros before you got to something else, initial and final are going to look exactly the same on your calculator. You're not going to see any difference in the initial and final if you just calculate those. And in a case like that, this would be the only way to get the answer. So that's the end of section 10. I'll go have my lunch. And unless something comes up, I'll do at least the first half of section 11. May have a different shirt on for the second half of section 11. We'll see how it goes.